In the last series of lectures, we have been examining unidirectional transport, where there is a variation in the concentration, temperature or velocity fields both in one spatial dimension and in time. Okay. And the general equation for the field variable, that is concentration, temperature or velocity, is of the form partial phi field variable by partial t is equal to partial by partial z of the diffusivity partial of to z plus any source, okay, where the field variable could be concentration, temperature or velocity, and you substitute the appropriate diffusion coefficient, mass diffusivity, thermal diffusivity or momentum diffusivity for D, and the appropriate source, which is a mass produced per unit volume per unit time for mass transport, energy produced per unit volume per unit time for energy transport. Of course, you have to divide it by rho Cp, and for momentum transport it is basically the force density, force per unit volume or momentum per unit volume per unit time. And you require two boundary conditions and one initial condition for this. So far we have restricted attention to steady transport, and we have considered cases where source is absent if there is no source. So, let me just write down the special case when there is constant diffusivity. Plus S. Okay. So, this is when the diffusion coefficient is constant, and in terms of the flux I can also write this as minus partial J z by partial z plus S, where J z is the mass flux for mass transport, the heat flux for energy transport, and it is the shear stress for momentum transport with a negative sign, because we have defined the shear stress as positive when it acts on the surface volume below the surface. Okay. So, and we considered various cases. First, constant diffusivity, no source, linear profiles, because the second derivative is 0. Constant diffusivity with a constant source, you get quadratic. Okay. The flux is linear, the field variable is quadratic function, as we saw for the flow down an inclined plane or the viscous heating. Flow down an inclined plane of a power law fluid, the constitutive relation is different from this one, but still this equation applies. The flux is still a linear function if the source is a constant. The flux is still a linear function, but the relation between the flux and the velocity, or the stress and the velocity, is nonlinear, and we saw how to solve that problem. Okay. Last class we had looked at a brief introduction to electrokinetic flow. Okay. This is a situation where you have two surfaces with a certain charge density on the surfaces. You apply an electric field along the channel, and there is a velocity along the channel. That is because the ions are localized close to the walls. So, the fluid containing ions is neutral in the bulk, but close to the surfaces which are charged, the ions preferentially concentrate, the ions of the opposite charge preferentially concentrate close to the surface. And so, you have a net charge close to the surface. The electric field acts on that charge and results in the net force, and that force generates a flow. That force density generates a flow. This surface charge is restricted to a length scale called the Debye length close to the surface. Okay. This is restricted to a length, a distance of the order of 1 Debye length close to the surface. And I had given you the formula for the Debye length and also the estimate for the magnitude of the Debye length. Okay. This Debye length is of the order of 1 to 10 nanometers for solutions containing 0.1 to 1 millimolar. Okay. It becomes large only when you have very dilute solutions. Okay. 1 millimolar it is about 10 nanometers, and 0.1 molar it is about 1 nanometer, and it becomes even less, okay, as you increase the ion concentration. And I had also defined the zeta potential, which is related to the surface charge density. Okay. And in terms of this, we had got an expression for the force density, which is basically the force, the electric field times the charge density, and this charge density is decaying exponentially away from the surface. Okay. This charge density is decaying exponentially away from the surface. So, you have to solve the momentum balance equation with this charge density. Since it is decaying exponentially from the surface, the force density is concentrated only very close to the surface. Okay. Away from the surface, the force density is 0. Okay. And from this equation, you can see that the curvature of the velocity profile, second derivative is the curvature of the velocity profile. Okay. The curvature of the velocity profile has to go to 0 far from the surface. It is non-zero only very close to the surface, within a thin region of the order of 1 dB layer close to the surface. So, if you have a symmetric channel and the curvature has to go to 0 far from the surface, that means the velocity profile is flat away from the surface, okay, because the curvature is related to the force density through this equation, second order differential equation. So, you have a flat profile far away, and very close to the surface you have this increase in velocity, which is exponential. Okay. We had got an expression for the velocity, which was a slip velocity times 1 minus e power minus z by lambda d. Okay. So, this is equal to 0 at the surface, and it increases exponentially to the slip velocity far from the surface. If you are considering length scales comparable to the channel height, this dB layer thickness is much smaller. So, basically on those length scales you will not be able to resolve this layer of the order of 10 to 1 nanometers close to the surface, and it will appear like a slip flow, okay, appear like a plug flow with a non-zero velocity at the wall. And we had estimated the velocity from this. Okay. Turns out this velocity depends on the zeta potential, it depends upon the electric field, okay, and it depends on the viscosity, does not depend on channel height, and it does not depend on dB layer thickness when written in this way. Okay. And I had shown you that this the magnitude of this velocity is actually small. Okay. It is not very large. Even for a 1 millimeter per second velocity, you require a very large potential gradient along the surface. Okay. So, the velocities that are generated are typically small, but they are useful nevertheless in applications where you want to drive a flow through channels of very small size. In this lecture, I will consider another system where you have a source or sink that is dependent on position, and that is the diffusion reaction system. Okay. So, I have a container in which I have fluid filled up to a height h. The height of the fluid is h. Okay. And you have a reactant in the gas phase, okay, that is diffusing into the fluid and reacting. Okay. So, it diffuses into the fluid and it reacts with a reaction rate reactant A, say, or A is equal to minus K C A, okay, where K is a first order rate constant. Okay. So, it is diffusing, and as it is diffusing through, it is also reacting. Okay. And we will use a coordinate system where z is equal to 0 is the bottom, okay. This is the z coordinate, and this is z equals h. So, reaction rate, mass consumed per unit volume per unit time is the reaction rate. Okay. Concentration is mass per unit volume. Therefore, K has dimensions of inverse time in this case. Okay. K has dimensions of inverse time. Okay. So, the governing equation for this steady state, okay, if we assume steady state is 0 equals d partial square C A by partial Z square plus S. Okay. And S in this case is the reaction rate, okay, is equal to d partial square C A by partial Z square minus K C A. Okay. Okay, so, this is the conservation equation and you can solve it. Okay. So, the way to solve it is that you write partial square C A by partial Z square is equal to K by d C A. And since this is a second order homogeneous partial differential equation, since there is variation only in one direction, I can also write these as total time derivatives. Okay. Because there is variation only in one direction. Okay. So, that means C A is some constant, okay, let me call it as C, okay, C e power root of K by d Z plus d e power minus root of K by d Z, okay, exponentially decaying and exponentially growing solutions. Okay. Now, what are the boundary conditions? Okay. The bottom surface is of course a solid surface. So, there is no diffusion at that solid surface, which implies that at Z is equal to 0, d J the flux is equal to 0. Okay. Flux is equal to 0 from Fick's law of diffusion implies that dCA by dZ is equal to 0. Okay. That is the boundary condition at the bottom surface. At the top surface, the gas is dissolving. Okay. If you have a gas dissolving into a liquid, then the concentration of the gaseous, the species A at the surface is going to be in equilibrium with the concentration in the gas. And if we assume that there is no resistance to transport in the gas, okay, typically the diffusion coefficient, I had recall that I told you that the diffusion coefficient in gas is typically much higher than the diffusion coefficient in a liquid. So, you can assume that the concentration is uniform in the gas because it diffuses much faster comparison to the concentration variation in the liquid. Then the concentration at the surface in the gas will be equal to the saturation concentration, the concentration in the liquid at the interface will be equal to the saturation concentration that is in equilibrium with the concentration in the gas or the partial pressure in the gas. Okay. So, this will be given by the partition between the gas and the liquid. Okay. So, at Z is equal to H, okay, the concentration C A is equal to the saturation concentration. Okay. So, we have to solve these subject to boundary conditions, these two boundary conditions. Okay. At Z is equal to 0, C A the derivative is equal to 0. Okay. So, therefore, you will get C root of K by d. I should use some other constants here. This confuses with the diffusivity. Okay. So, let me A and B. Okay. Equal to 0, which means that A is equal to B. Okay. Therefore, the concentration is equal to some constant into e power root of z root of k by d plus e power minus z root of k by d. Okay. So, that is the concentration. Okay. At z is equal to h, C A is equal to C S, okay, which means that C S is equal to A into e power h root of k by d plus e power minus h root of k by d. Okay. So, substituting this, the final solution that you will get for the concentration profile is C A is equal to C S into e power z root of k by d minus plus now, the flux at the surface, okay, the flux of A at the surface is equal to minus d partial C A by partial z at z is equal to h. This is the rate at which the material is being consumed by the gaseous species is being consumed in the liquid. Okay. That is the flux at the surface. Okay. So, I can write this as minus d into root of k by d, okay, into e power z root of k by d That is the equation for the flux. Okay. And then we can calculate the flux at z is equal to h. Okay. So, this is just the general flux. So, the flux at z is equal to h is equal to minus d C s root of d by root of k by d, I am sorry. That is the formal expression. Okay. We have managed to solve the equation and get the formal expression. The flux at the surface is given by this expression. Let us try to get some physical interpretation here. Okay. K has dimensions of inverse time. Diffusion coefficient is length square per time. Okay. So, this is a dimensionless group. Okay. This h root of k by d is a dimensionless group, which is the ratio of reaction and diffusion. Okay. The formal definition of the number is what is called the Damkohler number, okay, is equal to the square of this actually. Okay. K h square by d, okay, is equal to reaction rate by diffusion rate. Okay, reaction rate by diffusion rate. Okay, so, that is the dimensionless group. Okay. Now, this flux at z is equal to h has been expressed in terms of the Damkohler number. Okay. So, J A z at z is equal to h is equal to minus d C s root of k by d, okay, into e power Damkohler number power half minus e power minus dA power half by e power plus e power minus dA power half. Okay. Now that we have the flux, we can get the Sherwood number correlation. Okay. The Sherwood number, I can write it as Z divided by d Cs by H. Okay. If I assume Cs is the concentration difference, okay, the concentration scale, H is the characteristic length scale, the height of the film is the characteristic length scale, then this is equal to it is actually the magnitude, okay, because the flux is in the negative direction. So, this will turn out to be equal to H root of k by d into e power dA power half minus e power minus dA power half. Okay, so, this is the Sherwood number correlation for this particular case, and the prefactor here is actually Damkohler number power half. Okay. So, this is the final expression I get for the Sherwood number correlation. Okay. So, let me just write that here. And let us look at what physically this implies. Okay. First we consider the case where the Damkohler number is much smaller than 1. Okay. Which implies that h square k by d is much smaller than 1. That means that the diffusion rate is much smaller, is much greater than the reaction rate. Okay. If the rate of diffusion is much smaller than the reaction rate, okay, then the material will diffuse through the film before it reacts very much. Okay. It will diffuse through the film before it reacts very much. That means that the concentration variation is not going to be very large in this case. Okay. So, there will be a relatively small concentration variation in the film. It will be almost a constant. Okay. This is for the Damkohler number much less than 1. Okay. Another way to think of this is to think of this length scale. Okay. Okay. D by k per half is a length scale. Okay. It tells you how much the material diffuses before it reacts. Okay. So, you can consider this as a penetration depth. D by k per half is a penetration depth. It tells you how much the material diffuses before it reacts. Okay. The length scale for diffusion before reaction takes place. Damkohler number much smaller than 1. That means that the penetration, that the thickness of the film is much smaller than the penetration depth. Okay. So, that means that the material will penetrate all the way to the bottom before reaction takes place, before there is significant reaction. Okay. So, this can also be considered as the ratio of two length scales, the penetration depth, the height of the film square divided by the penetration depth square. Okay. So, the Damkohler number is equal to h square divided by lambda square, where lambda is the penetration depth. Okay. So, in this case it would penetrate almost to the bottom of the film. Okay. And I can for the Sherwood number correlation for this limit of small Damkohler number, I can expand in a series in Damkohler number. Okay. 1 plus dA power half is the expansion of the exponential. Okay. and the expansion of the second exponential is 1 minus dA power half, okay, in the limit dA very much smaller than 1, okay. And I divide this by 1 plus dA power half plus 1 minus dA power half, okay. Numerator, the 1's will cancel out, okay. In the denominator I can cancel out dA power half because it is much smaller than 1, okay, and in that case this just becomes equal to the Damkohler number, okay. So, that is the limit of small penetration, the limit where the penetration depth is much larger than the layer thickness. Damkohler number is much smaller than 1, okay, because Damkohler number is h square divided by the penetration depth square. Consider the opposite limit where the dA is much greater than 1, okay. The Sherwood number is equal to dA power half into e power dA power half plus when you have exponential of a large argument, e power minus x is much smaller than e power plus x, because e power plus x goes to infinity, e power minus x is 1 over e power x, okay. So, in this case I can neglect these two terms in comparison to the first term, okay, and the numerator and denominator, the ratio tends to 1, okay. So, I just get dA power half. The Sherwood number is equal to Damkohler number power half. Okay. What does that correspond to? Okay. dA much greater than 1 implies that h square by lambda square much greater than 1. The penetration depth is much smaller than the thickness of the film. That means that the concentration field is going to decrease very rapidly over a length scale that is comparable to root of d by k, okay. This is for dA much greater than 1, okay. So, in this case the penetration is restricted to a thin region close to the interface, and so the material reacts before it diffuses through that region, and therefore there is no solute below that depth, and all of the reaction takes place in a thin region comparable to the penetration depth at the surface itself, okay. So, this is an example of a reaction diffusion system, okay. We have a first order reaction and diffusion with a specified reaction rate, and in this particular case the source is a function of the concentration itself, because the reaction rate is a function of concentration. So, even though the diffusivity is a constant, the source is a function of the reaction rate, okay. And because of this we get exponentially increasing and exponentially decreasing profiles, okay, because it is a first order reaction. So, source is proportional to Ca itself, and we had rewritten this in terms of the Damkohler number, okay. So, we had got the reaction the solution for the concentration field, and from that we had got the solution for the flux at the surface, okay. And that was a function of h root of k by d, which is a dimensionless group, which is the square root of the Damkohler number, okay. So, and then we had just written the Sherwood number correlation, and you can see that it has a rather complicated expression. It is a function of Damkohler number power half with a certain specific dependence, okay, exponentials in the numerator and exponentials in the denominator. Nevertheless, we can check that this is correct by examining the limits of small and large Damkohler number and assigning physical interpretations to those. Small Damkohler number, penetration depth is much larger than the height of the film. So, the concentration is nearly a constant, and in that case the Sherwood number is equal to the Damkohler number. Large Damkohler number, the penetration depth is much smaller than the film thickness, okay, because Damkohler number is thickness square divided by penetration depth square. In that case, we find that the Sherwood number is Damkohler number per half. Okay. So, this is an example of a solution where there is a variation in the source strength with distance. Okay. So, this completes our discussion of unidirectional transport with constant diffusivity, with variable diffusivity, with no source, with constant source and varying source. Next lecture, I will start our discussion of binary diffusion. Everything we have discussed so far assumes that the Fick's law holds, that is, the flux is proportional to the concentration. Okay. This is valid only when the concentration is small in general. Okay. When concentrations become larger, there is a component of the flux which is due to the concentration variation. There is a second component because of convection. Okay. Convection due to velocity fields generated by the motion of the solute, okay, when the solute mass fraction or mole fraction becomes large. We will consider binary diffusion in the next lecture. I will see you then.